Okay, so we're doing section 8.1, solving systems of equations graphically. When solving systems of equations, the idea here is you're trying to find a solution that satisfies all equations that are involved. Okay. For a system of two equations, when you're solving, you're looking for an ordered pair that satisfies both equations in a system. There's really two types of systems that you'll see in this section. There's a type where you're combining a linear with a quadratic, so that's a line with a parabola, or you'll see a type of system called a quadratic-quadratic, okay, system of equations. Well, how many solutions might a system of linear quadratic equations have? Well, let me just draw a few examples for you, and then hopefully from the examples you can see the different number of solutions. So here's the first one. Well, let me draw the axes first. Okay. And by the way, when you're watching this video, if I'm going too fast, just press pause. If I'm going too slow, fast forward. Parabola, parabola, parabola. Here's the line. Here's the line. Here's the line. So notice the points of intersections are the number of solutions. So on the one on the left, we have 2 solutions. The one in the middle, we've got 1. And the one on the right, none. So no solutions. You might be thinking, well, how about a system of what they call quadratic-quadratic equations? Okay, let's do the same. We'll draw the axes, and we'll draw the 4 different possible scenarios. First, quadratic. Okay. I could have something like this, or something like this, or something like this, or something like this. So, how many points of intersections do you see? Looking at the one on the left, I see 2. Oops, not there. Here, 2 solutions. In this case, I see 1 solution. This one, no solutions. But then we have this interesting case where the 2 parabolas actually lie on top of each other. We call this infinitely many solutions. Okay, so these are the 4 different types of systems that you could see. Now, systems of equations can be solved graphically using the graphing calculator. I know some of you have one, that's great. Those of you who don't, look at this graphing calculator emulator and hopefully you can use it from there while you do your homework. On my test, I will give you a graphing calculator to use. But the idea here is you want to take each equation and solve for y, because the graphing calculator only allows you to write in equations that have, or that are in the form y equals to something. Input each of the equations, usually there's 2, into your graphing calculator, and then graph and find the intersection point. So I'd like to show you a few examples today. Okay, bring out your graphing calculators. Here are 2 equations. I'd like you to solve the following systems of equations using graphing technology. Okay, I'll bring out my graphing calculator, and let's take a look. Remember what we need to do first. We need to always solve for y. So let me label the equations. Here's number 1, here's number 2. If I were to take number 1 and try to solve for y, I'd like to move y to, or just keep it on the left-hand side. I want to isolate it. So I'm going to say negative y equals to, I'm going to bring the negative x, so the x over to negative x, and the 1 over to the right-hand side to make it -1. Don't like that negative, so I'm going to divide everything by -1. Y equals x plus 1. And that's what I'm going to ask you to type into your calculator. Turn the calculator on. Y equals 2. Let's delete all this stuff. X plus 1. Okay. Do the same with equation number 2. I will isolate y, so that's negative x squared plus 6x minus 3. Negative x squared plus 6x minus 3. So next equation, negative x squared plus 6x minus 3. Let's graph this out. Here's my picture. Okay, maybe you want to use the standard window for this one. That's perfectly fine as well. Okay. Don't forget to make a quick sketch of what you see on your graphing calculator. What else do I see? Oh yeah, line. That's y1. Parabola. Looks something like this. y2. My window coordinates, remember these are your x mins, x max, y min, y max. And to find the solution, go ahead and find the intersection point. First curve, second curve, third curve, not third curve, guess. So they give you the coordinates 1, 2. So that's one of your solutions. Remember, they are always an ordered pair because you have two variables now. And over here, 4, 5. 4, 5. Okay. Now, don't forget, you should also verify your solution. And verify means, well, you plug it back into the original equation to see if it makes sense. So we'll do that really quickly right now. Let's verify 1, 2. So what's our equations? X minus y plus 1. So x is 1 minus y is 2 plus 1. Does that equal to 0? Yes, that's okay. Let's also verify in the second equation. X squared minus 6x plus 3, I believe it was. Plus y plus 3. So plus y plus 3. Does that equal to 0? 1 minus 6 is negative 5, plus 2 is negative 3, plus 3, you bet. Okay. Don't forget to check the other one. 4 minus 5 plus 1 equals 0. Yes. 4 squared minus 6 times 4 plus 5 plus 3, does that equal to 0? 4 squared is 16. 16 minus 24, negative 8. Plus 8, 0, yes. So both work. Okay. Now, you try this next one on your own. It's the same as the one on the left. And I suggest you stop the video now so that you can try it on your own. And then come back when you're done to check your answer. Go ahead. So did you get these answers? I hope you did, because if you did, that's what I got to. Okay, I'm not going to check this one, but you should verify your answers always by just plugging things back into the equation. Okay, let's move on. Now here's a question where it talks about how engineers use these systems of equations to help them out. So engineers use what they call vertical curves to improve the comfort and safety of roadways. Vertical curves are parabolic in shape and are used to transition from one straight grade to another. Each grade is tangent to the curve. So suppose you've got surveyors and they model the two grade lines for a section of road to be those two equations. Okay, and then the curve is modeled by that. So think about, I've got a road. This is the equation. Y equals to negative 0.075x plus 6.103125. Got another road that goes like this. This is the upward sloping one, 0.08x plus 6.2. But of course, if you drive your car like this, you get a big bump down there. So what engineers decided to do was to try to smooth it out by drawing a parabola connecting the two parts. And this parabola is modeled by this equation. Okay. So it says, write the two system of equations that would be used to determine the coordinates of the points of tangency. Well, there's a left point of tangency and a right point of tangency. Looking at the one on the left, you'd be using these two equations, yellow, blue. So I guess that would be y equals to 0. Or I'll say y1, 0.075x plus 6.103125. And I'd also use y2, which is negative 0.002x squared plus 5.4. That's the point on the left. To find the coordinates of the tangent point on the right, oh, by the way, tangent just means touches at one point. Hopefully that's a quick review. Well, in this case, I'd probably make y1 the line in red and y2 the parabola. Okay. So I guess part B says they want you to draw that picture on the graphing calculator. So I guess I should just copy down the equations again. There's the line. Here's the parabola. And then there's the upward sloping line. Okay. Time to plug it in and graph. I'm getting tired. Once again, if I'm going too fast, stop the video. Okay, if I press graph right now using my standard coordinates, well, not so great. What can I do? Did I make a mistake here? Well, let's look at my window. Let's change my y min to 0, my y max to, let's say, 6. And let's see what happens here now. There's my downward. There's my parabola. There's my upward. I think I might have interpreted my original picture incorrectly. Anyone catch my mistake? Let me go back and change this again. If you can see what I did wrong, that's good. Because if you look at my picture now, there's the downward sloping, there's the parabola. Yeah. What's my problem? My problem is that that parabola is negative. So when I drew my picture, I drew it the wrong way. So let me just write down picture incorrect. Let's draw on the right one. Okay. Cross, 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 cross out. The right one should be down here. And notice what I have in my window. Negative 20, 20, 2, and 8. And look at the beautiful graph that I have. It looks like I've got a line going upwards, got a line going downwards, and I got a parabola in between like this. And once again, let's see if we can figure out the intersection points, because that's what part C talks about. So let's go ahead and do that with your graphing calculator. Second calc, choose number 5. Now notice I have 3 curves, so it asks, what's your first curve? Well, I want my first curve to be the line moving upwards, so I'm going to use my down arrow keys to try and toggle back and forth. That's the one I want. Press enter. I want my second curve to be the actual parabola, so I'm going to move down to that, press enter, and let's hope they find the intersection point. There we go. About negative 20, comma 4.6. So negative 20, comma 4.6. Similarly, we'll do the same thing with the other one. So second calc, number 5. This time I want to make sure I'm on the right line. See I'm on this downward sloping line, that's great. Let me just move it closer to the intersection point. Press enter, press enter, press enter. Okay, about 18.75, 18.75, 4.69. Great. So negative 20, comma 4.6, that seems to be this beginning one, and then the ending one. And interpret each point. Well, I think we talked about that earlier. Point on the left is where the upward sloping line meets the curve. And the other one here, of course, is where the downward sloping line meets the curve. Okay. Once again, the idea here is just to try to find out the intersection points, and we can use the graphing technology to help us out. Alright, last page. Last example, okay? This one talks about a performance of Cirque du Soleil and the heights above the seesaw versus the time for performers during a stunt. So, Cirque du Soleil does a whole bunch of different stunts. They say the two stunts are approximated by the parabolas as shown. Assume again that the second performer starts 1 second later or after the first performer, and their paths are actually shown on this coordinate grid here. So you see the first performer in green, and the second performer in blue. Here they're saying you come up with a system of equations that model the performer's height. So once again, you have to know the equation of the parabola. Let's go back to the good old days of chapter 3. In chapter 3, remember something called the vertex form, where a parabola is given by this equation, y equals to a bracket x minus p all squared plus q. Remember that p comma q is the vertex. A determines the expansion or compression vertically of the parabola. So let's look at the first performer. We'll do that one in green. I think we need to actually figure out the equation of that green parabola. And to do so, may I suggest you strongly look at the vertex. And I see that the vertex seems to have an x-coordinate of 0.75. So it's x minus 0.75 all squared. And the q value seems to be 5. Now to solve for a, we need to actually plug in a point. So let's plug in a point, and I'm going to use 0, 0 because that's pretty straightforward and easy to find a. 0 equals to a. 0 minus 0.75 all squared plus 5. Numbers don't look too nice. Nonetheless, gotta do it. What's 0.75 squared? So negative 0.75, close the bracket, all squared, 0.5625. So a equals to negative 5 divided by my answer, about negative 8.888. So that's about what? Let's change to fraction math, yes. Negative 80 over 9. Therefore, your equation for the first one is y equals to negative 80 over 9, x minus 0.75 all squared plus 5. First performer. Now you do the same thing for the second. Okay? I'll keep quiet. So if you look, the equation looks very similar, except instead of 0.75 as my p coordinate, it's 1.75. There are your two equations. Last thing, solve the system graphically using technology, and then interpret your solution. So you should sketch out your answer. I'm being lazy, so I'm just going to use my graphing calculator here. Okay. Negative 80 divided by 9, bracket, x minus 0.75, close the bracket, then we'll square it, plus 5. Do the same thing again, 80 over 9, x minus 1.75 all squared, plus 5. I will change the window to look like the one that was given in our notes, from 0 to 2.5 seconds. That's your x. And then how about from 0 for y to, looks like 6. Let's graph. There's the first performer. Here's the second performer. I want to find the intersection points. Second calc number 5. First curve, yes. Second curve, yes. Give me the intersection point. 1.25, 2.778. Or you can say 5 over 4. 2 and 7/8, 7, 7, 7, that's 7, 9. 18, that's I think 25 over 9. Let's just double check. 25 divided by 9. Okay. Interpret the solution. I guess that what it says is they meet at 1.25 seconds after the first deformer jumps, and they meet at a height of 25 over 9, and I guess that would be meters above the seesaw. Okay, that's it. You should be able to do your homework. Alright, so work on these questions, please. And hopefully you'll get this. Next day when we come back, we'll be looking at solving system of equations again, but this time using algebraic techniques. So goodbye, graphing calculator. But until then, enjoy.